Good morning, everybody. I know that you can't say good morning back, but that's the way these things often start. Welcome to this morning's session. For those of you that, and I know that the number of participants is joining just as we get started here on this Friday morning. My name is Todd Randall, and I am the Dean for the Faculty of Science and Environmental Studies at Lakehead. This has been, of course, been a very busy week here, an exciting week at Lakehead during our Research and Innovation Week, in which we've celebrated through a number of events, public talks, as we talk about the various research successes and contributions our faculty and students have made. One housekeeping point just before we get started. As is typical with these types of Zoom webinars, there will be an opportunity for you to ask questions. There is a Q&A box at the bottom of the presentation that you can type a question in. There will also be an opportunity to ask your questions verbally of our guest this morning at the end of the session, and he and our support will be able to help you do that if you'd like to do that. I'd encourage you to ask questions live. Thank you so much. This morning's research presentation is part of R&I Week's research showcase, demonstrating the important role that research plays in meeting the United Nations 17 Sustainable Development Goals. The session this morning, led by Dr. Pendia, relates to the topic of carbon sequestration. This is one of the solutions that could address, in part, increasing global greenhouse gas emissions across the globe. We are well served this morning to be having Dr. Florin Pendia deliver a keynote address on this topic, and it is my pleasure to, as his dean, to briefly introduce him this morning. Dr. Pendia is a physical scientist holding a faculty appointment to both the Department of Geography and the Environment and the Department of Sustainability Sciences on our Aurelia campus. He holds 2 PhD degrees. One wasn't enough for him. His first one is from his home country of Romania in quaternary geomorphology, and he holds a PhD in historical ecology from McGill University in Montreal. After which time he joined us in Aurelia in 2010. He is both a field and laboratory-based scientist and has embarked on a series of research projects both locally in Simcoe County and more extensively, including some work in Eastern Russia, with an overall research focus on the ecosystem and landscape responses to climatic changes observed during the Quaternary period, sort of the last 2.6 million years of Earth's history. Florin, like many of his colleagues, adapts a very student-centered approach as a faculty member, engaging senior undergraduate and graduate student trainees in research projects, as funding allows, of course, and bringing these important research ideas and findings back to his classroom teaching. It is my understanding that amongst his favorite courses is his capstone course, Global Climate Change, within both the geography and the environmental sustainability programs. His talk this morning is entitled The Future of Carbon Capture, From Local Efforts to Global Aspirations. I believe he will be discussing some of his recent projects locally in Simcoe County, set, of course, in the context of global efforts of carbon sequestration. Please join me in giving Dr. Pendia a warm welcome to the virtual podium. Thank you, Florin.
Thank you very, very much, Todd, for your introduction. Really appreciate you being here this morning. And thank you to the wonderful Research and Innovation Week team that has made this the series of webinars possible. And thank you all participants for tuning in this morning. It's a sunny, beautiful Friday morning, and really appreciate you coming in talking about carbon. So I will be starting to share my screen and kick off my presentation this morning. And my hope is really to bring to you a reflective discussion on the future of carbon capture. Of course, I'm going to weave in some of my own research that we have done here, our team has done here at Lakehead Aurelia, and really end up with hopefully a lively discussion on why carbon capture is something that we need to talk about, and how the discussion on carbon capture has become more and more personal for everyone. So my name is Florin Pendia, and as Todd said, I've been with Lakehead for over a decade now. And really enjoyed being part of the Lakehead team here in Aurelia, and my work mostly focused on climate change, as that would be a very broadly definition of it, but more specifically, I'm looking into ecosystem relationships, the relationship between ecosystems and the climate system. So a little bit about the relationship between the Earth's surface and the climate system as a whole. Much of my efforts in the last 20 years have been focusing on this, but I would like to speak with you or tell you about some of my most recent work in this field. So I'd like to give you an overview of today's discussion or today's conversation that I hope to have with you. Really, the way I framed my presentation is as a series of questions that I hope to allow us to sort of look at the topic from a variety of different angles. So first, we're going to try to address the question of why should we talk about carbon capture? So why is it important? And then, you know, a little bit about who drives the conversation in this on this particular topic, who drove the conversation earlier, who is driving it now. So a bit of a historical perspective there too. And then just quickly review, you know, the topic from the perspective of various ways in which carbon capture happens and how carbon is sequestered from the atmosphere where it does damage. We're going to look at this a little bit across a gradient from local to global, and in terms of the local efforts, I'm going to go through a couple of our own work here at Lakehead, and then we're going to look at this topic from a global perspective, particularly when it comes to today's environment, socio-political environment that is increasingly geared towards anti-globalization and rising nationalism. And finally, ending up a little bit of a rhetorical question, perhaps, can carbon capture make a difference? And I hope with this last question to stimulate some discussions that hopefully will involve all of you. All right, so why carbon capture? Well, as the saying goes, a picture speaks 1,000 words. So I'd like to answer or attempt to answer this question with one image, with one chart that really shows why we have this conversation now and why we are increasingly having this conversation, not just you know, amongst academics and scientists, but really throughout the larger community. The reality of today is that the last few decades we have experienced unprecedented climate warming, as this chart shows, with the last 2,000 years more or less being extremely different from what we are experiencing right now. So this chart basically shows the annual average temperatures for the last 2,000 years for the Common Era, and the baseline is the average for the 20th century. So as you can see here, almost all years in the last 2 millennia have been colder than the average for the 20th century, whereas the last few decades, 50, 60 years in particular, have been considerably warmer. So that is why we are having a conversation in a nutshell. Of course, The warmer world, the warmer Earth is due, and the scientists are now, vastly in agreement that the current warming trends that we're experiencing are due to greenhouse gas emissions that are produced by industrial and all kinds of anthropogenic activities. We talk about carbon because of these greenhouse gases, the vast majority of them, as you can see here in this graph, are carbon-based, namely carbon dioxide, which is making pretty much about 80% of all carbon emissions. And then there is methane, which also is a very powerful greenhouse gas that is carbon-based. So obviously, the carbon capture story comes from the fact that the majority of greenhouse gases are carbon-based, and therefore, whatever happens with the atmospheric carbon and with all the other carbon reservoirs is very important for this conversation. Now, as you probably all know, is that greenhouse gases are causing this warming because they act as an insulating barrier, which traps heat in the Earth's atmosphere. So, while this is, technically a good thing, we owe our, beautiful warm Earth to these greenhouse gases, because otherwise, without the greenhouse gases, the Earth would be a very cold place. It would be pretty much a snowball Earth. So this greenhouse gas effect, or a greenhouse effect, is essentially a good thing. But of course, too much of it and too fast of increase in the greenhouse effect can have detrimental effects on a variety of different systems within the Earth. And of course, it will affect, and it already started to affect, the human civilization as we know it. So who drives the conversation when it comes to carbon capture? Well, I think until about 2 decades ago, it used to be mostly scientists. And, some of them with their coming with their seemingly incomprehensible charts and maps. And but anyway, the scientific community has been, and it is now more than ever, unified in their assessment that the current greenhouse gas emission levels are unsustainable, and that if we don't do anything, the global changes that we are experiencing already and anticipating into the future may be irreversible, at least on a short to medium term. Now, scientists have worked closely together, but they also have been working with policymakers, and the UN has spearheaded this relationship some time ago with the foundation of the IPCC, which is the Intergovernmental Panel on Climate Change. This is a very important body that allowed scientists to have a policy platform in which they would assess the science and not only just produce the science, but assess the science related to climate change. So what were the scientists looking for? And really here, there are 3 main thrusts in which research has been sort of focusing on. And one is research on carbon pools, and this is where my own work falls into. So what does this mean? Well, really looking on observation into changes in the atmospheric, oceanic, and terrestrial carbon pools. Many scientists and researchers in general have looked into this for a long time, but a more systematic and focused assessment of these carbon pools is needed now because of the numerous feedback loops that exist between the atmosphere, oceans, and the terrestrial surface. Another thrust of, that research has been focusing on is related to greenhouse gas fluxes. Now here, the focus falls on observation on the distribution and variability of greenhouse gas fluxes between the Earth's surface and the atmosphere. Because look, essentially, carbon is good in the ground and it's bad above. The exchanges between the Earth's surface, including oceans and the atmosphere, are extremely important because we want this exchange to be a net positive for the Earth's surface and oceans, and a net negative for the atmosphere, because that's where greenhouse gases do most of their warming damage. And finally, another research direction is related to measurements on carbon cycle processes, particularly those that have an impact on greenhouse gas fluxes. So, you know, scientists have driven this conversation, but it becomes increasingly apparent that a bit of this conversation is shifted. Because you know, if you haven't been sleeping too much in the last year during this pandemic, and you spent time online or opening your TV, you've likely seen a bunch of news about carbon capture. And I think, you know, it's fair to say that when the bad boy of the tech world gets involved and throws money at the problem, that it must be important. Just recently, Elon Musk, for instance, put out an X Prize, as they call it, of $100 million, seeking sort of a competition, seeking new technologies on carbon capture. But look, it's really, you know, it's not just you know, very famous people, a lot of this in the business world, but it's just pretty much all science and technology sections of all major media outlets in recent years have brought this topic to the forefront. You know, so the conversation is shifted from the science and academic world to more of a mainstream interest. But why? That's the question. An important question is why has this conversation shifted? So I think one answer to this question is that the climate change has become very personal. And I really like this chart from Neil Kay with a Global Carbon Project. And so what this chart shows is the percentage, the ratio of all global fossil fuel emissions for the entire industrial era, which, as you know, started in the mid-18th century. So the ratio of these fossil fuel emissions that have occurred in your lifetime, in my lifetime, and everyone living today's lifetime. So let me give you an example. So if you are 85 or over, 90% of all global fossil fuel emissions have occurred in your lifetime. And that is the entire industrial emission that started since 1750s. If you're a middle-aged person, say 50, then 75% of all those emissions have occurred during your lifetime. Now, if you're a young person, let's say 30, half of all fossil fuel emissions have occurred during your lifetime. So I think this kind of shows how personal this has become to all of us, and it's no longer something we can overlook. But of course, this conversation has shifted also because the problem has become very costly. Now, just giving you a very recent, some examples of very recent events. You probably heard about the devastating wildfires of California and the costs associated with it, and the most recent climate emergency process that happened in Texas is really is raising the stakes basically on the topic of climate change, and specifically the unpredictability of climate that is a direct consequence of a warming world. And of course, some of these things are a little bit counterintuitive, and I'm not going to get into the discussion right now, but if there are questions at the end, I'm happy to discuss this further. But definitely we can see, the data here is from the US, is, not only is the largest economy, but also it is one of the most climatically challenged country in the world. So personal and costly, whenever these two items come into our conversation, I think it's easy to understand why this has now become a little bit more of a mainstream conversation and less of a sort of a exclusive academic field. Now, I should probably mention that this conversation is not without controversy. In particular, the discussion on whether or not technologies involved in carbon capture are hurting more than they're helping. I think there's been some discussion on that. And the reality is, though, that there are billions of dollars that are pouring in right now. And I think many of us are a bit skeptical when we're talking about all these billions. They're a bit skeptical about the real purpose behind these schemes. So I guess an illustration of how controversial this topic is if you go on Google and Google carbon capture, you would actually also get some of the most frequently asked questions by people. And I wanted to take a look at the first two. And the first one is, what are the negatives of carbon capture? So almost people are like, okay, it must be a catch here. There must be something the reverse of the coin kind of situation. And also, people are wondering whether or not this carbon capture is good for the environment. Now, of course, we can spend a lot of time talking about why people would think ill of carbon capture when it's seemingly a good thing, but I think a healthy dose of skepticism is not only important, but it's needed. So, but let us briefly go through some of the most important processes involved in carbon sequestration, carbon capture. And first, just to quickly define it, I'm sure many of you know this already, but just starting from a plain leveling field, carbon sequestration or carbon capture represent a suite of processes by which carbon dioxide is removed from the atmosphere or otherwise prevented from entering it. So, one of these types of processes are biological, and I think this one you're very familiar with. Biological processes, chiefly among them photosynthesis, is a process that basically absorbs carbon dioxide and then uses it to produce biomass, which is then later accumulated into the biosphere. Now, biological processes are very, very important. And of course, we talk about them all the time. But in terms of the narrower discussion on carbon capture, I want to sort of talk about these processes in terms of advantages and disadvantages. In terms of advantages for biological processes are no doubt the fact that these are natural processes. So, natural is generally very good. And also they don't cost anything. Plants will sequester carbon. And if we make sure that these biological processes are not disturbed, then it is likely an important way for which we can actually use these biological processes to increase and expand their capacity to sequester carbon. Now, there is a very important disadvantage of biological processes, and is that, as I call it, it's a two-way street. While photosynthesis absorbs carbon dioxide from the atmosphere and basically removes this greenhouse gas and sinks it into the soil, plants and animals die eventually. And when they do, a lot of that carbon returns back to the atmosphere. Aerobic decomposition processes will return to the atmosphere carbon dioxide, and anaerobic processes will go on the methane pathway, which is, for the record, methane is a far more powerful greenhouse gas than carbon dioxide is, and about 25 times more potent as a greenhouse gas than carbon dioxide. So obviously, when we discuss carbon capture into natural system in biological processes, we have to have both these conversations, absorption and emissions, because it is not just people that emit greenhouse gases. Nature, the earth, emits greenhouse gases as well. A second type of processes are geological processes, and these are very interesting because essentially we're talking about a variety of different minerals, particularly primary minerals of volcanic origin. Once they come to the surface, they undergo a process, a chemical weathering process, mainly through hydrolysis, in which these primary minerals decay to clay, which is a secondary mineral, and in the process absorbs a lot of carbon dioxide. So these are, large-scale processes. They're often ignored by the general public, I would say, and perhaps one of the reasons why they are not as well known is because they are sort of a little bit of a slow-moving type of process. Although I would bring again this conversation in a bit, because it looks like these long-forgotten processes are getting a new lease on life, and I'll discuss this in a bit. So what are the advantages here? Well, again, they're natural processes, and another very important advantage is that can be facilitated. So we can do something about increasing the effectiveness of these processes, and therefore the amount of carbon dioxide that is absorbed from the atmosphere in the process of weathering. Now, the disadvantage is, I would say there are no disadvantages, although a case can be made that because they're geological processes, they happen on a slower timescale. So perhaps their relevance is a little bit more medium to long term. However, that being said, some recent work looking recently over, as I do often, what's new in the literature, and an article in Nature recently published by Lemon and Possinger is that scientists are now working on ways in which we can actually, for instance, grind a bunch of volcanic rock and spread it over soils. This process will first increase fertility to these soils, and second, will kickstart a increasing chemical weathering process that will and has the capacity to actually compete even with some of the more classic carbon capture methods that are out there. So a very interesting and promising research that is of a recent nature. And of course, the third type of ways to sequester carbon are those that involve technological advances. So technologies by which carbon is extracted from the atmosphere and captured or isolated in a way that no longer poses a risk to the climate system. Now, there a whole bunch of them, and I'm going to go through some of them with you together. But basically, again, the advantage here is that as opposed to natural processes where we don't have full control, here we do. Is pretty much a matter of human human ingenuity that can facilitate this technological advances in the carbon capture process. Now, of course, disadvantages are pretty significant. Up until today, perhaps one of the biggest disadvantages that these technologies are extremely costly. And now there's some research pointing out the fact that actually some of these technologies may actually do significant harm as well. So again, it's all about a balancing act, I guess. But definitely we need more understanding on these processes in order to really see the advantages or the net effect that these technologies have on the overall environmental crisis. Now let me go through some of these technologies that we have today. And one of the most widespread, I guess, it's what we call a DAC, a direct air capture. So what this technology does pretty much sucks in air from the atmosphere and runs it through a cycle of carbon dioxide extraction. And then it isolates it, it concentrates into pure form, ready for storage or use. But there's a caveat here. Here it is. It uses water, renewable electricity, obviously if it's renewable, and natural gas. Now, I can make an argument that I don't think we can afford to use more of these resources, given the fact that many communities across the world are water challenged, electricity challenged, and energy resource challenged. So it is definitely a serious issue that that we have to explore fully. There is a direct air capture method that actually takes in carbon dioxide, but then lets nature takes its course. There are a couple of schemes, pilot schemes that have happened in Washington State, and there's another one, a major one in Iceland, which basically involves a industrial setup that absorbs carbon dioxide from the atmosphere, and then it sinks it into the geological strata where this carbon dioxide reacts with various minerals there and becomes stone. It's turned to stone, and therefore becomes inert. That is, no longer poses any risk of coming back to the atmosphere, at least not in short or medium term. Now, high tech and a little bit of a futuristic outlook is also, carbon capture can be used to produce very, very useful materials. Now, I don't know how many of you have heard about graphene. Graphene is an up and coming synthetic material that has been dubbed by Money Week, as you can see here, miracle material that will change the world. I don't know about that, but it's definitely something that, graphene is something that very well may be a material that your smartphone is going to be made of. And graphene is produced and can be mass produced by using carbon dioxide extracted from the atmosphere. So again, we can do here a bit of a two birds with one stone scenario. We're producing and innovating useful materials that are extremely valuable, and also use that as a mitigating climate change mitigation strategy. They're also what some people call designer molecules, engineered molecules that are trained to pretty much absorb carbon dioxide from the atmosphere and then release it in controlled environments. Quinone is one of these molecules, but there's a lot of recent research expanding this field. So it's a very exciting research happening in a technological realm. But I mean, it's really, I think the conversation that one would have here is that it bears down to two issues. One is an issue of choice, and then the other one is an issue of scale. Now, in terms of the choices we have, the question is, do we go natural? Do we choose biological processes as a way to enhance carbon capture and mitigate the increasing level of industrial or anthropogenic greenhouse gas emissions? Now, again, it's a good question. Certainly I believe that whatever strategy we choose, biological processes involved in carbon capture are going to be critical to that effort. Do we go on a sort of a geological scale? And I think there's a fair point here that while these are very useful and large scale, they're also kind of slow. So it may not be that effective when it comes to this immediate crisis we are dealing with right now. Or do we innovate our way out of this mess? Are we going to just invest in technologies and really focus on put all our eggs in this tech basket? But I think it's I think a sensible answer to this question would be that perhaps we can just do all the above. There's no reason why we can't. And then there is an issue of scale, which how do we go about it? Do we go local? Like lots of local initiatives that we hope will amount to something greater. Hopefully, sort of a sum that is greater than the a big thing that is greater than the sum of its parts, or do we attempt to go both local and global? So these are very important questions that, of course, we should explore. So now I just want to give you some examples of some local efforts, and in particular of two of our own initiatives and partnerships here at the Aurelia campus. One was a partnership between us and Lake Simcoe Regional Conservation Authority and focused on wetland carbon, and I'll explain a little bit about it. And then the second one was a smaller project, a pilot project that dealt with carbon in urban turf. This was a sort of a bit of a community-based research, and I'll explain a little bit about both of these. So our project with LSRC involved a comprehensive study on wetland carbon throughout the Lake Simcoe watershed. So this a little bit about this project. Of course, probably you're wondering why wetlands, and it's a fair question. Wetlands are, like many other ecosystems, extremely capable of absorbing carbon dioxide, and therefore, they are an important asset in this, global biospheric fight to absorb more of this carbon. But unlike other ecosystems, when wetlands have an ability that not many other ecosystems have, which is to store carbon long term. Because we love forests, we all do. For instance, we love planting trees, and we know that planting trees will result in absorption of carbon dioxide. But the problem with trees is that eventually they die, and when that happens, most of their carbon goes back to the atmosphere. Wetlands, on the other hand, have the ability to kind of undergo a process of lock and throw away the key kind of scenario. So they're able to store carbon long term. So our focus started with wetlands, but is by no means the only ecosystem we're interested in. In fact, there's some good news that I just received today that might kickstart some future projects on different other ecosystems. So what was the research question here? Well, it's a pretty straightforward question, and our question was, which wetland ecosystem has the highest capacity to absorb carbon dioxide and store it long term? So what are we doing it for? Well, for a variety of reasons. Of course, more science is always valuable, but the main rationale for our project was that many jurisdictions across this country and frankly across the earth need more understanding of watershed scale processes that could aid in formulating effective greenhouse gas emission policies. So Lake Simcoe Regional Conservation Authority has spearheaded a series of actions, climate action initiatives that sit at the core of these of the need for more effective policies. And personally, and for us as scientists, a special interest was that we needed more information and more insight into potentially coming up with engineered ecosystems, basically wetlands that will be engineered for the purpose of carbon capture and other purposes, because wetlands are not just a valuable ecosystem in terms of the fight against the greenhouse gas crisis, but also as valuable habitats for biodiversity and other purposes. So as most of you know, Lake Simcoe watershed is situated in South Central Ontario. It's about 3,400 square kilometers surface, which is about 0.3% of, it's a tiny surface of the Ontario province overall land surface. Wetlands, however, make up about 52,000 hectares, which is a little bit over 15% of the watershed. So not a lot, but there is a diversity of ecosystems here, with swamps being the most widespread, but then we also have marshes and submerged aquatic environments, fens and bogs. So a whole host of different ecosystems that we have investigated to find out which of these are the most effective carbon capture systems. So what we found was actually pretty interesting. As you can see here, marshes are by far the most productive, the most capable of absorbing carbon dioxide, with net pools, for instance. I'm sure if you live in Southern Ontario or in Simcoe County, you probably live within about 10 kilometers of one of these cattail marshes that are spread all over our county and throughout the watershed. These marshes are actually very productive, and ironically, actually the most productive is the one dominated by Phragmites, which is an invasive species, as you know. Is that long feathery grass that you see on the sides of highways and in wetter areas of our neighborhoods. So yeah, it's an invasive species, but look at it. It's very, very effective in absorbing carbon. But pretty much all of these ecosystems are good carbon sequesters. On average, the watershed has about a pound of carbon, pure carbon sequestered for every square meter of wetland surface. So that's the watershed average. And this amounts to about 0.6 megatons of carbon dioxide equivalent. Now, you would probably be curious, well, what does that mean? Like, is that a lot? Is that a little? What is the what is the terms of comparison? And you know, if we're looking at it, you know, it's a 0.6 megatons of carbon dioxide equivalent. That's how much these sequester annually. Well, the province of Ontario emits about 159 megatons of carbon dioxide equivalent. So you might think that's very small, and it is. You know, when you look at it superficially, it's about just 0.4% annual offset. But remember, the surface of these wetlands represent a very, very, very small amount of the total surface of Ontario. It's just about 0.05%. So it's a pretty good offset considering it comes from such a tiny surface. And another thing that I want to put in perspective is, you know, how much is this, you know, sequestration when compared with other more familiar perhaps systems. And here you have the Canadian forest average sequestration potential. As you can see, most of these wetland types in Southern Ontario fare much better. So they're more capable of absorbing carbon dioxide than forests are. And I can make an argument that it's not just that they can absorb more, but they can actually store it long term, and that's why we engage into this process. But there is a catch. And I mentioned it earlier that, you know, dead plants are a source of greenhouse gases because decomposition processes eventually will return a large part of the carbon sequestered back to the atmosphere. So pretty much as kind of canceling things out. So we have to look at this issue very carefully, because when we say something is good, we have to make sure that it is truly a good carbon capture device or technology or process. So what we did was to look into the long-term carbon sink assessment of the watershed, and in particular to really investigate what is the actual measure of lock and throw away, the key scenario for the wetlands in a Simcoe watershed. What we found when we investigated this long-term rate is that bit of a slightly different picture, really, because it has to do with different communities, plant communities being more able to sequester carbon. For instance, bogs are actually the least have the least potential of sequestering carbon, but are actually long-term, they are the most able to do so. So, you know, the values are here much lower, as you can imagine, with a total sink of 24 megatons of carbon dioxide equivalent, and we'll put this in perspective in a minute. So our carbon balance here is that out of almost a kilogram of carbon and the net primary productivity of these wetlands, 55% of that is lost in the first year back to the atmosphere. And for the next 100 years, 2/3 of this initial pool is actually lost back. So it looks bad, but it's still something that, you know, it's a net. We can characterize these systems as a net sink, which is what's really important. In terms of equilibrium time, it is about 60 years. Within 60 years of a plant dying, basically, it stops emitting carbon dioxide. So these wetlands show a net sink after about 60 years until this, you know, sink is becoming pretty much stable, and therefore we can consider it as a long-term storage scenario. Of course, there are some of these environments that are more chaotic, so not all these models are so straightforward, but definitely overall wetlands have this extraordinary capacity to be a long-term carbon sink. Now, fair question, is this sequestration significant? Is this just a drop in a bucket? Of course, when you look at it, you know, the wetlands of Lake Simcoe watershed sequestered about 24 megatons of carbon per century, and this is not much when we consider that Ontario emits annually about 159. But again, when we think about the fact that this comes from a very tiny surface and there are many dozens of similar watersheds across the province, these values all of a sudden look a little bit better. Anyway, we also had engaged, started a pilot project on urban turf. And here we looked to investigate the capacity of urban lawns to sequester carbon. And another very important task here was to raise awareness and seek community involvement. And I have to say that it's been a really it's been such a tremendous positive experience. The community and you know have responded in a very positive way. Lots of citizen scientists out there that are really interested in and wanted to get involved. I can talk about this a little bit more at the end if there are any questions. But really getting to the you know, from the local perspective to the global one is really important, and particularly when we talk about the current atmosphere of anti-globalization and rising nationalism. So how do we tackle this giant that is global warming? There are a couple of models. The first model I call the David and Goliath model. It's really about large multinational initiatives that act under one voice, and there's a lot of opinions out there that say a global problem needs a global solution. And you know, the example of the Paris Accord is you know, one of the most recent in the line of these large multinational initiatives. And of course, there's definitely something to talk about. But there is another model, and I call this model the Gulliver and the Lilliputians model because it's pretty much framed around a variety of national initiatives with loosely connected themes. Now, there's a lot of hope involved in this model, and one part of this hope is that we will get you know, sort of a cumulative effect of all these national initiatives, hoping that they will amount for something greater. And also, we're also counting on the cooperation of the giant, very much like in the beloved fairy tale. You know, we hope the giant will cooperate, maybe you know, counting on some of these homeostatic capabilities that the climate system has built in that will help us fight the issue. So can carbon capture make a difference? Yes, I think the simple answer is yes, but we need a much more accurate cost-benefit analysis, particularly when it comes to the pricing of carbon emissions. And I think there's a case to be made that it has to make a difference because we may not have much of a choice. So do we hope? Do we think this? There's hope in the future. I think so, but I think this hope is also about a nascent new generation, that perhaps a generation that will refuse greenhouse emissions, will refuse to be complicit in this onslaught of greenhouse gas emission, and perhaps, you know, stop producing them, and even you know, work with their dollars in the sense that they can buy products only that have been produced by using these emissions, or in a way that does not produce emissions. So anyway, so this is it for me today. Sorry, I took a little bit longer than I thought, but thank you very much to everyone. Merci miigwech to all for tuning in, and I want to acknowledge the financial support from LSRC and Lakehead University VP Research Strategic Funds that helped us with the carbon project, urban carbon project. And I particularly want to thank my co-investigators, Dr. Kanavalil and Kuri Sherry, our very, very important lab support folks, Dr. Tabrouge and Dr. Menon, and our wonderful students and volunteers, Andy Tomei, Johnston, Godden, Grimaldi, Khan, and Dia. And now questions.
Hi, we have a question here for you from Andrew. In terms of reducing carbon in the atmosphere, how much of an impact of the gradual introduction of electric cars have over time?
Yeah, that's a really good question. And really, I think that I'm just going to stop sharing now, so we can have a conversation. I think the electric cars are probably one of the most important steps that we need to take, and I think we're all very happy to hear that there's been sort of a more recent acceleration of the process. And I was very happy to hear that our own Oshawa plants here in Southern Ontario are going to start producing electric vehicles, and I think that's a very important. The acceleration of electric cars is very important because cars are responsible for two very, very serious greenhouse gas emissions, and that is carbon dioxide and nitrous oxide, which is extremely powerful greenhouse gas, much more powerful than carbon dioxide is. So there's, of course, there are a whole host of different ways to do it, but I don't think there's just one. Obviously, our driving cars is today one of the things that we need to change. There's no question about it.
Thank you. We have a question from Nicole. Great presentation. I'm curious to hear more about how the general public is using their lawns for carbon capture.
Yes, you'd be surprised. Actually, I didn't get a chance to go too much into detail there, but you'll be surprised that our lawns, the very lawns in front of our houses, are actually very good at capturing. They're almost as efficient as forests. And I know that's hard to believe, but that's true. Now, of course, there's a caveat there, and the caveat is that it depends on what you do with your lawn. If you were fertilizing it too much, if you're tending, manicure it too much, and using chemicals and other things, the benefits may actually be outweighed by the damage. But in essence, our very own lawns are actually able to sequester quite a bit of carbon. It's about 200, I think it was an average for really, I was about 238 grams of carbon per square meter of lawn. That's a pretty cool one, because forests, for instance, the average Canadian forest are sequestering about a little bit less than 300 grams. So it's not bad when considering that this is an urban environment, usually not thought of as a good for climate. But of course, there are a lot of caveats there, but a lot of more research needs to be done. There's not a lot happening right now, but more and more urban emissions policies are factoring in these potential of carbon mitigation for urban environments. So there is potential.
Perfect, thank you. We have two more questions. First being from Paul. Should LUFA and the university divest its pension fund from fossil fuels to send a signal that the fossil fuel age and carbon emissions must end?
I think so. I think there is a very quick answer from me. There is that yes, we have to, because I think the only way this global effort can succeed is if we look at the money issue, or wherever the money is involved, there's of course the potential for us, paying more attention to the short-term gains rather than the benefit of all and the long-term gains. So the answer is yes. Now, of course, this is a difficult issue. I'm sure that LUFA and the university is considering very carefully. But personally, the answer is unambiguous yes.
Thank you. And our final question is from Victoria. How do we encourage governments to take carbon into consideration when looking at development?
Well, I think, and you should watch out for LSRC, Lake Simcoe Conservation Authority. They really are one of the conservation authorities most advanced in their climate change mitigation plans that involve a lot of these conversation around carbon capture and carbon sequestration. And I think that governments are more and more linking new developments in particular, with at least a carbon neutral kind of setup. I know the York region has recently been interested in exploring new developments around carbon neutrality. And I think that the more we talk about this and the more this becomes a mainstream issue, the more governments, because the voters will demand, right? So that's how this has to happen.
I think we have time to squeeze in one more question here. The photosynthesis process is probably the most efficient way to proceed on the global scale. Is this the way to resolve the real problem? The wetland surface is negligible worldwide.
Sorry, can you repeat the last? I think there was a bit of interruption. The last statement.
The wetlands surface is negligible worldwide.
Well, actually, it's not. The wetland surface is significant, and in fact, wetlands overall store about 1/3 of the entire planet's soil carbon pool. Even though surface-wise, yes, they're only about 4% or 5% total, they store 1/3 of that carbon that exists in the soil. So they are phenomenally important. But there is again a catch with wetlands. Wetlands, if heated, if disturbed, they actually may switch from being a carbon sink into a carbon source. And particularly when it comes to anaerobic processes such as those that lead to methane production, because I mentioned earlier that methane is actually much more powerful as a greenhouse gas than carbon dioxide is. But in any case, one of the major concerns right now in the wetland science is that global warming has actually shifted some of these wetlands from carbon sinks into carbon sources, and actually adding to the problem rather than being a solution to the problem. So again, research is growing every day, but more needs to be done. And the reason we did this project here in Southern Ontario is that we wanted to move away from this focus that is currently mostly on peatlands, and focus on other type of wetlands, such as the mineral soil wetlands that we are so blessed to have here in Southern and Central Ontario as well.
Thank you very much. That brings us to a close of our session this morning. I would like to thank Dr. Pandya for sharing this valuable information with us. It was a pleasure to have you participate in Research and Innovation Week 2021 virtually.
Thank you, everyone, and thanks again for tuning in. Merci, miigwech.
Everyone, please enjoy the rest of your day. We have 2 more sessions as we bring this week to a close. We hope to see you there. Thank you and enjoy your day.